Hi, I'm Nihal, and I will be presenting our work on zero-shot learning with common sense knowledge graphs. This work is published in Transactions on Machine Learning Research. Zero-shot learning is the task of predicting classes without any labeled examples. During training, we learn model parameters with class representations on a labeled dataset containing seen classes. During testing, the trained model along with the class representations are used to predict unseen classes that are disjoint from the seen classes. Class representations are descriptions that enable us to transfer from seen to unseen classes. Several types of representations have been proposed in the past. Some of them are handcrafted attributes, pre-trained embeddings, and sentence embeddings. One increasingly popular method is learning class representations from knowledge graphs. They have achieved strong results on zero-shot object classification in ImageNet. They offer the structural power of handcrafted attributes and the flexibility of pre-trained embeddings. They represent the nodes of the graphs as classes and learn a graph neural network to get a vector representation for the node. But these methods learn class representations with the WordNet graph. The WordNet graph is specialized in object type hierarchy and may not provide rich features suitable for a wide range of tasks in multiple domains. We propose to learn class representations with common sense knowledge graphs. Common sense knowledge graphs are a large-scale source of high-level information. They typically range from 100,000 to 8 million nodes and 2 million to 21 million edges. These graphs have free-form relationships between the nodes that can be useful for a wide range of tasks in multiple domains, which we will show in our experiments. The natural question to ask is, can we use existing graph-based frameworks to work with common sense knowledge graphs? Existing graph-based zero-shot learning frameworks have several limitations. GCNZ requires the entire graph structure during training. That is, GCNZ is not inductive. Since we know that common sense knowledge graphs are large, training a graph convolutional network on the entire graph can be prohibitively expensive. DGP requires a directed acyclic graph. In a common sense knowledge graph, we are not restricted to a directed acyclic graph structure. To address these limitations, we propose the ZSLKG framework. ZSLKG is a zero-shot learning framework that learns class representations from common sense knowledge graphs. We learn class representations with a novel graph neural network called the Transformer Graph Convolutional Network, or TRGCN. TRGCN learns a transformer-based aggregator in the graph convolutional network layer to compute a nonlinear combination of the node neighbors to capture complex relationships in a common sense knowledge graph. TRGCN is an inductive graph convolutional network, which means we don't need access to the entire graph during training, allowing us to scale to large-scale graphs. Now, I will describe our architecture in detail. We use a bilinear similarity model, which is a simple architecture commonly used in zero-shot learning. On the left-hand side, we have the example encoder, which is the task-specific encoder that accepts text or image as an input and produces a vector representation. In this example, we use a BiLSTM with attention for the fine-grained entity typing task. On the right-hand side, we have the class encoder, which in our case is the Transformer Graph Convolutional Network. In this example, we have a two-layer graph convolutional network with a half-specific transformer aggregator. After the messages from the node neighbors are passed through the graph convolutional network layers, we map the classes to the learned node features and treat them as our class representations. Then, we take the dot product between the example representation and the seen class representations to get the compatibility scores or the logits. Finally, we train both the example encoder and the class encoder by minimizing the task-specific loss over the true labels. In this example, we use a binary cross-entropy loss as fine-grained entity typing is a multi-label classification task. During inference, we use the trained transformer graph convolutional network to get representations for the unseen classes and perform zero-shot classification. We consider 6 datasets across 3 tasks in language and vision. We compare ZSL-KG to WordNet-based baselines that use graph convolutional networks. Our results on fine-grained entity typing and intent classification show that ZSL-KG outperforms existing WordNet baselines on all 3 datasets. Our results on object classification shows that ZSL-KG outperforms WordNet baselines on 2 out of the 3 datasets. Overall, we outperform WordNet baselines on 5 out of the 6 datasets. In conclusion, we introduce ZSL-KG, a flexible framework for zero-shot learning. We develop a novel transformer graph convolutional network that captures complex information in the graph. Our results show that common sense knowledge graphs are a powerful source of high-level knowledge. For more details, please visit our project page.